So let's understand why brute forcing WPA2 is a very time-taking process. Like it's a very long process. In order to understand that, you need to be understand the process of WPA2 handshake, like how the password is authenticated between the access point from the client. So let's understand WPA2 and which is a four-way handshake. So, um, let me just. So this is how the process will be happening. Let's say this is your access point, and this is us, the client. So the way the handshake happens, I mean the authentication process happens is first the access point, the router generates a random number called a nonce and sends us to the client. Like whenever we type in our Wi-Fi password and click authenticate, the first thing the access point do is perform the announce. I mean generate a random number and it will send to us. After getting the announce, the actual process gets started here on the client side. So after getting the announce, what we do is we generate a similar random number called s nonce. So using these a nouns and s nouns will be helpful to declare a will declare a hash that will be valid for a time period. Like we can validate this is the same um, handshake happened for a particular time period. So after generating the S nodes, we will generate our pairwise master key, which is PMK. The way PMK is generated is performing the HMAC hash based authentication code of a SHA-1, which is a combination of our password plus the SSID, the router access point's name. This process is performed using PBKDF2 password based key derivation function 2 on 4096 iterations. Like it creates a PMK master key. From this using master key, we generate a PTK pairwise transient key. So the way the pair is transient key is generated by is combination of the PMK plus AP MAC address plus client MAC address plus announce plus snouns. We will combining all these and we will generate the pairwise transient key. From the PTK, we will generate our KCK. Is just a chunk of 16 bytes, the first 16 bytes of the PTK. It will be first 16 bytes. See, the first 16 bytes of the PTK is the KCK. So now we will combine these KCK and an empty EAPOL request for space to add our MIC, which is the main thing we require. The MIC is for message integration check, and it is a combination of this CKC our MTEAPOL request on HMPC SHA-1, and from this we will take the first 16 bits, the one bytes, it will be 128 bit key, I mean hash key. So this will be the 16 bits bytes of thing. Once the MIC is generated, we will send this MIC to this person. Mm, So this MIC will be sent back to the access point. This is the first action. This is the second action. After this goes here, the same process gets to happen over this side of the same process of generating the MIC. This time the access point uses our S nouns and it's A nouns and generates the same MIC. Made a mistake here. And this will be generating the same 16 bytes of key. After generating these 16 bits of bytes of key, it will compare both the keys and make sure if it's same, then it will send us the GTK group temporal key, which will be used for our encryption of a broadcast or multicast traffic. So this goes to here, and this is the third action. Now we will send an acknowledgement back, basically back to the client, telling that we have installed this group temporal key for authentication. So whenever you enter a password in the Wi-Fi field and you tell to authenticate, this is the whole process. A announce is generated. From that A announce, S announce is generated, followed by a PMK, which is the process of 4,096 iterations of both our password and SSID in the PBKDF2. We generate the PMK. From PMK, we will combining the MAC addresses of both the devices and their random generated numbers, announce and S announce, which will be generating our pairwise transient key. From this pairwise transient key, we will generate the CKC, which is just a first 16 bytes of a chunk from the PTK. Then we will perform the SHA-1 hashing of our this 16 bits and an empty EAPOL request, because we need to send back this with the MIC. If we include the MIC in the EAPOL, it will create a loop, infinite loop within the uh, generation of hash. So we will leave some empty space and add this, and it will generate a message integration check. From this, we will take the first 16 bytes and append this to a EAPOL request and send this to the access point. In here, it performs the same action, the same whole action, like wait, copy, paste, and this guy on this side performs the same thing. Just yeah, this guy performs the same action over here using our S nouns and every rest of the things, and generates the same MIC, and it performs the comparison over here, like comparison of MIC. Once the comparisons of the both MICs is okay, is okay, if it's valid, then it will send us an group temporal key, which will be used for encrypting the broadcast and multicast traffic for the rest of the process. I mean, the rest of the communication in between the access point and client for taking the back and forth of the traffic. After taking this key, we install it in ourselves in the client side and send an acknowledgement of we have installed the keys. Now we are ready to transfer data. So in order to brute force this whole thing, in order to brute force this whole thing, this whole action going on here, we cannot uh, directly take the password and compare, because through the medium of transferring, there is not at all a single time we are transferring any plain text or any hint of text. Everything going around is encrypted. I mean hashed. So except these a nouns and s nouns, which are just random generated numbers to define whether they are the same authentication process being happened. So now the process we are going to take on to perform brute forcing of this whole thing is we will generate this MIC individually, like for every time. Once we capture this four-way handshake, like once we capture this four-way handshake, we will grab these information, like it's a network traffic conversation we capturing. We can publicly, I mean, plain in the plain text format, we can find this a nouns, s nouns, and obviously SSID, MAC addresses will be easily extracted. Then we will perform the same action using different, like numerous permutations of this password. So the basic number of characters required for WPA2 is 8. We'll be using 8 characters. See, 8 characters. Let's perform some math. So how many permutations will be generated for 8 characters? Let's let's see, for 8 characters of numericals, only the numbers, 8 to the power of 10. Yeah, it's a decent number. We can perform brute forcing of it easily. So the process goes like this. We be generating the MIC through the whole process, and we will compare this, like for every password we be adding our permutated password, generated password in here, and perform the whole process and take that information and compare with the MIC inside the four-way handshake. We need to go through the whole process every time until we will find one that matches our MIC. Yeah, this could be possible if the person using only numericals. Let's say if the person used just capital letters along with the numericals. In such a case, we be having 26 capital letters plus 10 numericals. Then it would be 36. We have an enormous number which is in exponential form, so high that even if you take time to brute force it, it takes a long time. The reason of taking a long time is this thing, the PVKDF2. That is the main culprit in here. The PVKDF2, the password based key derivation function 2, which is created keeping in mind that it should take more computationally high effort to generate it hash. So it takes it, even if you have a basic computer, it takes a long time to perform this action over and over and over to uh, create n number of hashes to compare with. Let's say even if you generate 1,000 keys and compare them in a second, it would take a lifetime to compare them, like that how many. But the professional tools like hashcat, John the Ripper,
what they do is instead of using a CPU to make this process compute, instead they use directly the GPU. GPU has many cores compared to CPU. It will perform these math calculations very fast, like algorithmic calculations, whatever required for the hashing. It performs very fast, even though it does speeds. If the person uses, we have just calculated this thing for 8 characters. What if the person uses a 12 or 14 characters password? It's an exponential growth of that number. It's a very high exploded number that it takes a long, long time to crack that password. Instead of doing all this brute forcing, the best possible way to find is social engineering, because we humans are the weakest part in the segment of a system, of a security system that is easily vulnerable and exploitable. So better you think about a social engineering way to exploit this rather than wasting your lots of effort and time to crack through a password. If you know what type of characters, how long uh, the text can, the password phrase can be, then it would be significantly, we might have a chance of cracking it. But if you're not sure about it, then it would be a very time taking process. Also, you'll be needing high computation to perform these actions. Even if you buy a VPS, rent a VPS with the proper GPUs and perform the action, it would take a long time. For the amount of money you'll be spending on to perform the computation, you might get a decent internet connection. Peace.